Hello, everyone. So welcome to Physics 207, the Physics and Movement Science Lab. This is Lab 2 on measurements of space and time. So basically what we're going to do in this lab is two things. We're going to measure the density of a small aluminum cylinder. And to do that, we're going to use an instrument called a vernier caliper. All right, and I'll explain how to read a vernier caliper in a little bit. Now, if you're watching this because you're making up the class or it's a snow day, then I will give you the data for the height and diameter of the cylinder, and I'll just have you do the calculations. However, I still want you to know how to read a vernier caliper. So I'll go over that in this video. I'll walk you through how to read a vernier caliper. All right, but since obviously you can't measure the height and diameter directly because you're doing this remotely, I'll give you that data. All right, so that's the first thing, finding the density of a small aluminum cylinder. The second thing that we're going to do is look at the relationship between the period and the length of a simple pendulum. And again, since we can't collect data in class this week because of a storm or if you're out, what I'll do is I'll have you collect the data using a simulation. And again, later in this video, I'll walk you through how you do that, how you can use the simulation so you can collect your data. And then the graphs you can do as usual on Pasco Capstone. Okay, so to start, this is what we need to do. We need to measure the height of the cylinder 5 times and the diameter 5 times. Again, I'm giving you the data here. Normally you'd have to collect this data on your own. And the instrument that you're going to use is a vernier caliper, but at least let me show you how you would read the vernier caliper. Okay, so here's a model of a vernier caliper. And notice that there's basically two scales on the caliper. You have a main scale that goes from 0 to, I think it goes to 12 centimeters. It's in centimeters. And you have a vernier scale, which is on one of the jaws here, the one that moves, that slides. It goes from 0 to 9. So let's say you have some object, this blue object here, and you want to measure the length of the object. Then you first put the object in between the two jaws, right, of the vernier caliper, close it down. And then to read that length, what you're doing is you're reading where the 0 here is on the main scale. Like, where is this 0? This is sometimes called the index. Where does that 0 lie on the main scale? Well, if you look at this, you can see how, like, this is 1.0, this is 1.1, 1.2. It looks like it's 1.2 something, right? Because it's in between 1.2 and 1.3. And just by eyeballing it, it doesn't look like it's quite halfway. So it might be like 1.22, 23, 24, something like that. So to get that last digit, the hundredths place, so this vernier caliper, its resolution is 0.01 centimeters, right? So you can record it to 2 decimal places. So to get the hundredths place, the second decimal place, what you do is you look on the vernier scale and you ask yourself which one of these marks, the 0, the 1, the 2, the 3, and so on, lines up best with any line from the main scale. We already know it's probably going to be like 2, 3, or 4, just based on where it is, because it's not quite halfway. And if you look at this, it looks like the third line lines up best. So then you would read this as 1.23 centimeters. That would be the length of this object, okay? And actually the computer records it over here, 1.23. That's what they got as well. All right, let's try another one. Let's say, okay, so now let's say this is the new length. So you have a new object, right? You want to measure the length using the vernier caliper. So in this case, if you look on at the 0 here, right? Where is this located? Well, in this case, it's located past 2.1, right? It's in between 2.1 and 2.2. So it's 2.1 something. It's more than halfway. So it might be like 2.1, 6, 7, 8, somewhere around there, 9 maybe. To figure out that last digit, you're going to look on the vernier scale and ask yourself which one lines up best with any line from above. And we know it's probably going to be like, 7, 8, or 9 based on where it is. So I'm going to focus on 7, 8, or 9. And it looks like in this case that the 8 lines up best, right? So I would read this as 2.18 centimeters. Okay, that would be that length. All right, let's do a couple more. Let's say this was your measurement right here. No, it's not moving. Hold on a second. Okay, so now let's say this is your new length. So now what is this actual length? Well, the 0 is right on 2.2, right? So you would say it's 2.2 something. Well, the 0 lines up best. So that last digit, the hundredths place, would be a 0. So you'd actually read this as 2.20 centimeters. Okay, let's try one last one. Let's say this is the length that you want to measure. So in this case, see how the 0 is just past the 2? So actually you'd read that as 2.0 something. It looks like it's just about halfway, maybe 3, 4, 5, somewhere in there. Again, to get that last digit, I'm going to look on the vernier scale. In this case, it looks like the 4 lines up best. Sometimes it's really hard to tell. I would say probably the 4 lines up best. So I would read this as 2.04 centimeters. Okay, so that's how you read a vernier scale, vernier caliper. Okay, so for your group lab report, the first question that you're responsible for is question 4. Remember, all these questions refer to the questions from the lab manual. In this case, it's lab 1, right, in the lab manual, which you can find on Brightspace. And basically, I can paraphrase it right now. This question is going to ask you to describe how you use the vernier caliper to measure the height and diameter of the cylinder. Like, how did you read the vernier caliper? So based on what we just talked about, you can describe, a few sentences how you read the vernier caliper. Okay, then you're going to measure 5 measurements of the height, 5 measurements of the diameter. Okay, so in this case, I give you those measurements, right? So here are the 5 measurements of height. Let's say we went through the measurement process with the vernier caliper. We got these 5 measurements and these 5 measurements of the diameter. So question 5 is make sure you include all the data in your table, right, as usual. And I want you to calculate the average height, the average diameter. Make sure you round those to 2 decimal places, right? Because that's the resolution of the instrument. It's 0.01. And then I also want you to calculate the percent relative average absolute deviation, the PRAD for height and the PRAD for diameter. So that's question 5. Fill in this data table, the rest of this table, calculate average height, average diameter, and the PRAD for height and the PRAD for diameter. And make sure on your group lab report that you show me the calculations for the PRAD for height and the PRAD for diameter. What I'll do at the end of this video is I'll walk you through a sample lab report, like what this first group lab report should look like. Okay, so you have a better idea of exactly what I expect for a group lab report. Okay, then we get to question 6. Question 6, I want you now to calculate the volume of that aluminum cylinder and the PRAD for volume. So the question is, how do you do that? Let me go over to the iPad and show you this more carefully. Okay, so first thing, a cylinder looks something like this, right? This is like a right circular cylinder, where this is the radius, this is the height. And we know that the volume of a cylinder is equal to the area of the base, which is a circle, right? So it's pi r squared times the height. However, in our experiment, we didn't really measure the radius, we measured the diameter. So let's rewrite this equation in terms of the diameter. So we know that the radius is equal to half the diameter, right? Diameter divided by 2. So if I substitute this in for r here, then I can rewrite the volume as pi d over 2 squared h. And then if you work that out, that's going to be pi d squared h over 4. Okay, so that's how you're going to calculate the volume. You're literally going to plug in your average diameter, your average height, work it out, and that will give you the volume of the cylinder in centimeters cubed. All right, the second part of question 6, right, the second row of that table is to calculate the PRAD for volume. Well, remember how PRAD works when you have an equation that involves either multiplying, so in this case, we're multiplying a bunch of variables or dividing variables. This is also true if you divide variables. The pi and the 4 have no error, so you can ignore those numbers. It's just the variables, right? The diameter and the height here. So you can think of volume as really being proportional to diameter times height, right? Because it's d squared times h. And remember, the rule is if you want to calculate the PRAD for the volume, and you have a formula that involves multiplying or dividing variables, then the rule is you have to add these respective PRADs, right? If I want the PRAD for the dependent variable here, PRAD for volume, I have to add these respective PRADs. So in this case, and we learned this in week 1, right? So this is going to be PRAD for diameter plus PRAD for diameter plus PRAD for height. And that will give us the PRAD for volume. Okay, so let me go back to the handout here. So remember, ultimately, our goal here is to calculate the density, right, of the cylinder, of the aluminum cylinder. So now we're going to jump to question 11. And the first thing you need to figure out is you need to find the mass, right? In order to compute the density, we need to know the mass and we need to know the volume. We just found the volume. Now we need to figure out the mass. So normally, if you were in the class, I just have you weigh the cylinder on a little electronic scale. Here, I gave you the data, so you have the data. Now you have to be a little careful. This scale, its resolution is 0.1 grams, right? It's only 1 decimal place. So the first part of question 11, I want you to find the average mass, right? So average these, make sure you round to 1 place, find all the absolute deviations, and then average those, right? Round to 1 place, and then calculate PRAD. Now remember, you have to use at least the resolution of the instrument here, right? So when you average these, if this is less than 0.1, you have to use at least 0.1. Right? So be careful with that. And then remember the PRAD is going to be your average absolute deviation divided by your average mass times 100. Same thing up here. If this average, when you average these, if this is less than 0.01, because that's the resolution of the vernier caliper, then you have to use at least 0.01 here for your average absolute deviation. And then the PRAD would be 0.01 divided by your average height times 100. And the same thing for the diameter here. If you forgot this, go back to the measurement handout that we went over in detail in lab 1. Look at that again if you forgot how to calculate PRAD. Okay, so again, find the average mass, find the PRAD for mass. Make sure you show me the calculation, right, for the PRAD for mass. Then the last part of question 11 is to calculate your density. This is like your experimental density. And then we're going to find the PRAD for density, and then we're going to compute the percent experimental error. We're going to compare our value to like the gold standard for the density of aluminum. So again, let me jump back on the iPad and show you how to do these 3 calculations, how these work. Okay, so to compute the density, usually we represent density by the Greek letter rho. So this stands for density. And I'll write EXP for experimental. It's our experimental density. You're going to take your average mass that you found from above, right, the table above, and divide that by the average volume that you calculated from above. And that will give you your experimental density. So it's just mass divided by volume. To compute the PRAD for density, this is similar to what we did earlier, right? Again, remember, whenever you have an equation and it involves either multiplying variables or dividing, in this case, we're dividing. The same rule holds if you're dividing. If I want to find the PRAD for this dependent variable here, then I have to add these two respective PRADs. So this is just going to be the PRAD for mass plus the PRAD for volume, which you have, again, calculated above. All right, that'll be the PRAD for density. And then finally, the third thing that you had to compute in that table, right, the third row, is the percent experimental error. That's when you compare your value to the gold standard, right, which we're going to assume today is 2.70 grams per centimeters cubed. That's the gold standard for the density of aluminum. So if I want to compute percent experimental error, then remember I take my experimental value minus the gold standard. So again, we're going to assume it's 2.70. I make it positive, right? So absolute value. So the difference, but make it positive. And then remember, the key thing is you have to divide by the accepted predicted gold standard value, which is a 2.70, and then times 100. Okay, so that will allow you to compute all those values that you need for that table for the end of question 11. And make sure you show me those three calculations in your group lab report. Okay, so that's it for the density of the aluminum cylinder. The second part of the lab is we're going to investigate the relationship between the period and length of a simple pendulum. So normally, again, I have you collect the data using a physical pendulum, like a real wooden pendulum in the lab. However, in this case, I'm just going to have you collect the data using a simulation of a simple pendulum. In fact, in some ways, it'll come out even nicer. All right, so let me bring up the table so you can kind of see what data you need to collect. So for each of these lengths here, when the pendulum is 10 centimeters, 20, 30, 40, 50, what you need to collect for data is you need to get the time for 10 oscillations, 10 complete oscillations of the pendulum. And then the last two columns I'll explain later, you can calculate these values. So this is the important column right here. This is the data that you need to collect using the simulation. So let me go to the simulation right now and I'll show you how you set it up so that you can start collecting these values. Okay, so click on that link. It'll take you to this page right here. This group right here from University of Colorado, they make some really good physics simulations. In fact, we'll use several of these throughout the class this semester. So this one, I'm going to click Start. Right, it brings up the simulation, and we're just going to use the intro part of this. So just click on Intro. And in terms of the instruments we need, we don't actually need the ruler. I'm going to click that off, but definitely need the stopwatch. I'm going to move that over here. And then we can adjust the length of this pendulum using the slider. So remember, you're going to be doing this for 10 centimeters, which is 0.1 meters, right? So that'd be 10 centimeters. And then 20, 30, 40, 50, right? For those lengths. So let me just demonstrate this. I'll just pick one of these, say like 30, something like that. The mass doesn't matter. You can leave that here and you can leave all these settings. This is the only one that's going to change because you have to find the time for 10 oscillations for those 5 lengths, right? 10 centimeters, which is the same thing as 0.1 meters, 20 centimeters, 30, 40, 50. Okay, so to collect the data, I'm going to hit pause here. Let me bring this down closer. I'm going to displace the pendulum by some small angle. It doesn't really matter how much, maybe 20 degrees. So I'm going this way, so it says -20, that's fine. Then I'm going to press start on the timer. So it's ready to go. And now when I press the play button here, it'll start oscillating and I need to count the time for 10 oscillations, right? So it's going to, one oscillation means it's going to go all the way over to this side and then back. That would be 1, and then 2, and then 3. And when it hits 10, you want to stop the timer. You want to get the time for 10 oscillations. So if I'm going to hit start and then kind of hover over this so I'm ready to stop it, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. So 11.22 seconds. That would be the time for 10 oscillations when it had a length of 30 centimeters. Okay, so you're just going to do the same thing, but for all 5 lengths. And by the way, if you want to reset this, you can just like pause it. You can reset the stopwatch, set it at the beginning, so negative 20 degrees. Hit start first on the stopwatch so it's ready to go, and then press start again and it'll start oscillating again. So you're going to get the time for 10 oscillations for those 5 different lengths. All right, let me go back to the handout. Okay, so we have the time for 10 oscillations, right? And all these should be to 2 decimal places. So make sure you round all these values to 2 decimal places. So once we have that, how do we calculate the period? Well, remember, by definition, the period is the time for 1 oscillation. So if I take this value, the time for 10 oscillations, and I divide by 10, that'll give me the period, right? That'll be the time for 1 oscillation. By the way, the reason why we collect the data for multiple oscillations is to account for the fact that there could be some error in like the reaction time. So this kind of like mitigates that error because we're doing multiple oscillations. All right, and then once you have the period, these will be rounded in 2 places. You're going to square them to get the last column here, right? This last column is just the period squared, right? So you're just going to square these values to get that last column. Okay, the last few questions involve a couple of graphs and then 1 equation. So question 16, if you look in the lab manual, and you should go back, you should always refer back to the lab manual to make sure you have the complete question. You're going to do a plot. You're going to plot period versus length, right? You're going to do this on Pasco Capstone. So period will go on the y-axis and length will go on the x-axis. All right, let me jump on the iPad to kind of show you what this should look like. And then actually, let me go ahead a little bit and then I'll do both of these. And then question 17 is you're going to plot period squared. So this last column versus length, right? So again, period squared is on the y and length is on the x. And then finally, question 18 wants you to come up with an equation that gives the period as a function of the length. I'll explain this on the iPad in a minute, like how you can come up with this equation here. Okay. All right, so again, question 16 is going to be a graph of period versus length. So period will be on the y-axis. That'll be in seconds. And then length will be on the x-axis, and that'll be in centimeters. And you want to make sure you also include the 0.00. Okay. It turns out that this graph will look like a square root function. Right? It'll look like kind of like a sideways parabola. Like when you plot your data, you're going to get something like this. You want to do a square root fit. And actually, I'll jump on Capstone in a little bit and show you how to do this fit here. Unfortunately, it's not one that we can select. Normally, we can just select the fits. Square root is not an option, so I'll show you how you can get Capstone to actually do a square root fit. So plot period versus length and do a square root fit. And then don't forget to answer the last part of that question. So in addition to doing the plot, it'll ask you like, what is the shape of the curve? You can say, you know, it's curvilinear, it's a sideways parabola, it has a square root fit. However you want to describe it, make sure you describe the shape of the curve. Okay, question 17 is going to ask you to plot period squared versus length. And that turns out to be linear. So when you plot period squared, so now I have period squared which is seconds squared versus length. Again, make sure you include 0, 0. This one you're going to find is linear. So let's say that's your data. You want to do a linear fit. Right, so this is a linear fit that you can just choose from the menu of options, right? Linear fit is one of them. And the important thing that you're going to need from this is the slope. Remember, it'll give you a box of information, and one of the things it'll give you is that slope value, the m. Okay, you're going to need that for question 18. Okay, so question 17 is do that plot. It'll ask you what is the shape of the graph. You can say it's, linear. And then you're going to need that value, that slope value for question 18. So what is question 18? Question 18 wants you to come up with an equation that gives the period as a function of the length. So when I worked with the other lab groups this week, I kind of walked you through this. So I'll walk you guys through this as well. So if we look at this graph, this period squared versus length, it's linear, right? And what's the most general way that we can write the equation of a line? Well, we could write it as y equals mx plus b, right? It's a slope-intercept form of a line. And the b is the y-intercept, which in this case is 0, right? Because this graph is like basically, you should find it goes right through the origin here. So the b is 0, we're going to eliminate that b. The y variable is what's plotted on the y-axis. And what do we have on the y-axis? We have period squared, right? So period squared is like our y variable. Usually we denote period by t, like capital T. So y is basically t squared, right? Period squared. And that equals m times the x variable. Well, what's plotted on the x-axis? If we look on the x-axis, we have length, right? So the x variable is just length. Let's give it a name. Let's call it like L for length. So I'll just call this L. So right now we're close, right? We have t squared equals m times L. What we want is we want the period as a function of the length. So the question is, how do we find the period if we know the period squared? Like mathematically, how do we get the period if we have period squared? To do that, you simply take the square root, right? Take the square root of both sides. So if I take the square root, it's really plus or minus, but we're going to take the positive square root. I'm going to get t is equal to, and I can write this as the square root of m times the square root of L, right? Remember, if you have the square root of, say, a times b, in general, you can write it as the square root of a times the square root of b. So I can write a square root of m times square root of L. This slope here, so this m, remember, this is the slope of your period squared versus length graph, which you have right here. You have that value. When you plotted period squared versus length, it gave you that slope value. So what you can do is you can plug this value in for your m here. And then you can simplify that. It's just going to be a number, right? Square root of some number. That'll give you a new decimal number, whatever it is, times the square root of L. So that'll be your answer. This is just going to be a decimal number. It'll probably be about 0.2. So I'll say about 0.2, but it depends on your data, right? It'll be close to 0.2. So question 18, when it asks for the formula that gives the period as a function of the length, that's what we want. We want this equation right here. T equals some value around something around 0.2 times square root of L. Okay, so what I want to do is kind of just quickly show you how to do that square root function because it's not one of the options for the fit. So I just jumped on Pascal Capstone, right? Remember, when you use Capstone for graphing, you should just go to Classic Templates and then click on this upper left-hand one here, the one with the table and the graph. And then for your labels, right, you go to Select Measurement, Create New, User Enter Data. I'll call this Length. And then I'll hit Tab or Enter and do cm for the unit, centimeters. Then I'm going to click on Select Measurement, Create New, User Enter Data. Let's call this period. Hit Tab, and I'll say S for seconds. And then I'm just going to make up some data that will lead to like a square root function. Let's say my data is like 0, 1, trying to think of numbers that'll work here. 4, 9, 16, 25. That'll work. And then my period values, let's say, are 0, 1.1, 1.9, I don't know, 3.2, 4.1, 5.0. Let's say those are my values. So to plot this, remember I go to the x-axis and I choose what I want to plot on the x-axis, which is length. I choose the y-axis, what I want to plot on their period. Right, I can move this out of the way, but if you do that, see how it dims it? You make sure you click on it again so it's highlighted. And then for the title, remember the easiest title to give it is the y variable versus the x. So I can call this period versus time. And then I don't want these line connections, right? So remember from week 1, to get rid of these, you hover over a data point, you right click, it'll bring up this menu, and you uncheck show connecting lines. Okay. And then normally to do the fit, it's this icon, right? Make sure you turn it on. If you turn it off, right, make sure you turn it back on. And then the arrow here allows you to choose what fit you want. Unfortunately, a square root is not one of these options. So we're gonna, there's a way of telling it that you want to do a square root function. What we're gonna do is we're gonna do a user-defined function. So this last one here. So I'll click on user-defined. By default, it assumes it's a line. So this ax plus b is like mx plus b, right? It's the equation of a line. We need to change that. So to change that, you click on that information. On the left-hand side of your capstone, it'll bring up this curve fit editor, which I can click on. And I want to change this formula here. So right now it's ax plus b. So I'm going to change that to a times, I'll leave the times there. And then I'm going to do sqrt, like for square root, open parentheses, x, close parentheses. So a times sqrt of x. Then if you hit apply, it should do the fit. Okay, great, it did that. You can get rid of this menu here just by clicking on curve fit editor again, it gets rid of it. And that's exactly what we want, right? So now it's doing this square root fit to our data. So make sure you include this graph in your group lab report. And to do that, remember you hover over the border here, the blue border, you right click, go to copy display, and then you can paste it into a Google Doc or whatever you guys are using to share when you're working on your group lab reports. Okay, and then the second graph is more straightforward, right? The second graph was period squared versus length. So now period squared will be on here, length, but then you can just choose linear, right? It'll do the linear fit when you choose linear. It's only this first one where it didn't have a square option, so we had to do that user-defined option. Okay, so that'll allow you to do your 2 graphs. Okay, so the last thing I want to go over is I just want to show you what I expect for a good group lab report. So first thing, make sure you have a cover page, right? First of all, everything needs to be typed, right? So you want to make sure you type up all your lab reports. And the first page is just a cover page where you have the name of the experiment. So you can just put lab 2, measurements of space and time. And then make sure you include all your lab partners' names here, right? There's either 3 or 4 people per group, right? I forget your exact groups, but make sure you include all your lab partners' names here. Okay, then I'll scroll down here. You're just answering those questions from the lab handout, which refer to the questions in the lab manual. So remember, question 4 was describe how you use the vernier caliper to measure the height and diameter of the cylinder and how you read the vernier caliper. So you want to write something like this. Obviously, don't give this to me exactly back, but you can paraphrase it, right? Something like this would be fine, right? A few sentences describing how you read the vernier caliper. Question 5 was include all of your data, right, in the table. So again, I gave you guys the height and diameter, but you have to include all the other data, right? Do all your calculations. You don't have to show me like the absolute deviation calculations or height, but make sure you show me the final calculations, like the PRAD for height and the PRAD for diameter. So I showed those 2 calculations here. If you should do everything in the computer, but if you find it difficult to do the calculations in the computer, you could write them down neatly and then take a picture of it and then put the picture in your group lab report. Or you could even leave a blank space. When you print it out, you could write them in neatly. That's fine. Or you could just do them on a computer. It's up to you. As long as it's done neatly, that's fine. But most things should be typed, right? The only exception is maybe the equations. If you really don't want to type it, you can write it. All right, so that was question 5. Question 6 was include this table, right, of data. and then calculate the volume and the Pradford volume, and then make sure you show me those two calculations, right? So I have those two calculations here. Then we jump to question 11. We're definitely not doing every question. There's a lot of different parts of lab 1, so we're just jumping around. So question 11, make sure you include the table of data for the mass, right? Calculate the average mass, the PRAD, the percent relative average absolute deviation for mass, and show me the calculation for the PRAD for mass. And then the end of question 11 was this table here with the density. So again, show me this calculation for the experimental density, show me the calculation for Pradford density, and show me the percent experimental error calculation where you compare your value to the gold standard of 2.70. So I have those 3 calculations here. Okay, then we go into the pendulum part, right? So again, make sure you show me the table of data, right? All of it should be to 2 decimal places. Remember, this data you got from the simulation, and these you can just calculate. I did like a sample calculation here for period and period squared. Maybe you could do like 1 sample calculation. That would be fine for the first row. Then question 16 was that period versus length graph, right? When you plot period versus length, you could either cut and paste it right here, or what I did, I just attached it to the end and I said, please see graph, but you can copy and paste it into the lab report right here. That's fine, right, with question 16. But don't forget to answer the question about the shape of it, right? You could say it's a sideways parabola, curvilinear, however you want to describe it. Question 17 was your second graph, right? That was period squared, this column versus length. So you can just copy and paste it right here, or you can add it to the end. It's up to you. Again, don't forget to answer the question about the shape. And then question 18, remember we had to come up with an equation that gives the period as a function of the length. So we came up with this equation, t equals the square root of n times square root of l. But now you're going to plug in your slope value that you got from your period squared versus length graph, right, from question 17. In fact, if I go to the graph right here, remember that m is this value right here. So 0.0412 is my m. You're going to probably get around 0.04, right, somewhere around there. So 0.0412. Don't worry about this error term here. You just need that first number. So I plug that in for m here, and when you take the square root of 0.0412, I'm going to get 0.203. Remember I said ultimately you're going to end up with something around 0.2-ish. So that's my final equation. The period is equal to 0.203 times the square root of L. Okay, and then again, I attached my graphs to the end here. You could just copy and paste them right at the question itself. It's up to you how you want to do that. So your group lab report should look very similar to this sample lab report, right? You want to make sure you show everything I did, except you're going to have your values, right? So it'll give you a good idea of what I expect for a good group lab report. So I would work on this this week and try to do as much as you can. Because of the snow day, basically we have a snow day, I won't require you guys to actually submit your group lab report next week. I'll give you an extra week. So if you have any remaining questions, we can talk about them next week. All right, if you have any remaining questions, we'll talk about it next week. So I'll give you an extra week, but you should really do all the work and make sure you have all this done. If you remember your group partners from last week, you can contact them and work on this together, or you can do it individually. And then I'll give you an extra week so you'll have time to put together this group lab report. When you submit the lab report, just one person from your group is going to print it out, make a hard copy, and bring it to lab the following week. Okay. But again, we can talk about this more next week. Just make sure you get all the work done, and we'll figure out how to get your group lab report done. Okay. Hopefully that was helpful.